On the morning of November 18th, something changed. After weeks of silence, the data from NASA's deep space telescopes finally aligned, and what they revealed was not the expected decay of a dying object. It was coordination, precision, pattern. 3I Atlas, once labelled a faint anomaly beyond Mars, had just done something no known comet or asteroid has ever done. Instead of disintegrating, it stabilised. Instead of drifting randomly, it made what now appears to be a course correction. And at the heart of that motion lay something far more unsettling, a signature, artificial, periodic, and deliberate. For the first time, even the most cautious voices inside NASA began to whisper the same question. Is this an alien spacecraft? At precisely 04:12 UTC on the morning of November 18th, a signal emerged that no one expected, and no system was ready to explain. The event was first captured by a narrowband sensor node aboard NASA's Deep Space Network, then mirrored in real time by the Subaru telescope in Hawaii, the Cabrera station in Spain, and Gaia's L2 orbital platform. Each independently registered the same signal, a short-lived, highly focused burst in the near-infrared range, pulsing for a duration of 5.93 seconds, with a rise and fall envelope so smooth that one observer described it as surgical. But this was not just a flare. It was not chaotic, explosive, or entropic in nature. It bore the statistical hallmarks of modulation, intentional control over frequency, amplitude, and timing. When analysts overlaid the data on top of the rotational telemetry for 3I Atlas, the findings became even more unsettling. The burst occurred precisely as the same surface feature, identified days earlier as a reflective notch along the object's equatorial ridge, faced Earth for the 6th time in a 66-minute window. That meant one thing: this wasn't a spontaneous emission, it was part of a pattern. The bandwidth of the burst fell between 10.5 and 12.1 microns, a range commonly used in Earth-based optical communication and ranging systems. Specifically, it sat inside a narrow spectral band utilised in military-grade satellite LIDAR and deep space telemetry. That coincidence raised immediate questions within both civilian and defence communities. Could this be a false signal, a bounce or artefact from one of our own systems? But no satellite in Earth orbit, nor any known outbound probe, was positioned to produce such a return signature. The emission was narrow, coherent, and spatially locked, originating from 3I Atlas itself. The nature of the waveform revealed even more strangeness. Using Fourier decomposition, signal analysts broke down the pulse into its base harmonics. What they discovered was a recursive structure. 3 peaks, followed by a plateau, then a mirrored 3-peak inversion before a clean drop-off. This is not how natural bursts work. Solar flares, chemical outgassing events, or electromagnetic interference all show random noise, spikes, decays. This pulse, in contrast, behaved like a file header, an envelope designed to bracket data or frame a repeated pattern for decoding. More disturbing was the timing. The burst coincided with a complete radio blackout in the local space surrounding the object. ESA's solar orbiter, positioned millions of kilometers away but still within vector view, registered a temporary suppression of background noise, suggesting a kind of signal dampening field activated during the emission. No signal got in, no signal got out. For the duration of the burst, 3I Atlas became acoustically invisible, except for that single blinding whisper through the infrared. Several institutions hesitated to release early conclusions. The word artificial was considered but avoided. Instead, internal memos used the phrase coherent directional event. It didn't matter. The shape of the signal, its bandwidth, and its synchronization with the object's rotation all pointed toward one terrifying possibility. This was not a geological emission. It was a functional transmission. Some researchers compared it to early spacecraft beacons, where a base carrier wave would pulse with no clear message, only to indicate presence. A ping in the dark. Others likened it to optical handshake protocols, where 2 systems align and exchange cryptographic keys before transmitting real data. But the most unsettling hypothesis came from an MIT group studying the rotational harmonics of the object. Their model showed that the next identical burst, if part of a loop, should arrive in 66 minutes. It did, and then again, and again, each precisely timed, each slightly stronger than the last. The object wasn't just broadcasting, it was checking for a reply, and still, none came. When observing any natural interstellar object, particularly one on a hyperbolic trajectory, scientists expect a degree of chaos. Rotational drift, axial precession, and surface tumbling are all well-documented behaviours in comets and asteroids, especially those subjected to uneven heating, gravitational perturbations, or residual momentum from prior collisions. But in the case of 3I Atlas, none of that happened. Instead, as the object approached its closest observational window, it exhibited one of the strangest physical behaviours ever recorded in deep space: complete rotational locking. From November 16th to November 18th, observatories from 3 continents monitored 3I Atlas during a phase of intense solar exposure. Across over 60 hours of continuous tracking, employing both visual spectrum and mid-infrared sensors, the same face of the object remained pointed toward Earth. This wasn't an approximation. This was near-perfect orientation, confirmed down to arcsecond resolution. Normally, a comet's surface spins due to the momentum it has carried since its formation, often altered by asymmetric sublimation or outgassing events. These forces should have caused 3I Atlas to exhibit some variation in rotational behaviour, wobbling, slowing down, or at the very least shifting its facing orientation by a few degrees. Instead, it behaved like a satellite in a 3-axis stabilised mode. Infrared readings showed that heat was being emitted consistently from the same points on its surface, particularly along an equatorial ridge that researchers began calling the signal belt. This consistency allowed scientists to triangulate the object's orientation using thermal mapping overlays from ESA's Gaia tracker and NASA's Infrared Telescope Facility, IRTF. The data was startling. There was no axial wobble, no torque-induced roll, no differential heat bloom. The object wasn't spinning randomly, it was holding steady. More precisely, it was holding a pose. When translated into relative space coordinates, the object's orientation was found to align within 0.04 degrees of a fixed vector between Earth and the Sun's barycentric gravitational midpoint. That isn't just improbable, it's architecturally suggestive. Maintaining a locked orientation relative to multiple moving bodies requires a balance of forces that has only been achieved in engineered systems, such as geosynchronous satellites and Lagrange point observatories. Theories began to circulate. Was 3I Atlas simply rotating very slowly, giving the illusion of orientation? This was dismissed after tracking showed repetitive infrared emissions every 11 minutes from the same physical surface features that never moved. Others proposed gravitational capture or magnetic locking, but no planetary body was near enough to produce the stabilizing torque required. Instead, one possibility rose to the top: internal inertial stabilization. In advanced aerospace engineering, inertial dampening or gyroscopic stabilization is used to maintain a spacecraft's attitude during flight. By spinning a set of internal masses at high speed and adjusting their axes, engineers can control the exterior orientation without requiring external thrust. But such systems require sensors, logic, and energy, a coordinated infrastructure. So why was a supposed comet exhibiting behaviour that mimics satellite-grade inertial locking? Microwave background noise readings taken from the Goldstone complex offered a chilling clue. Every 66 minutes, coinciding with a full signal cycle noted the previous day, a faint polarization shift occurred in the object's magnetospheric wake. This shift, though nearly imperceptible, repeated consistently with the thermal pulses. Some researchers theorized that this shift could be caused by internal field cycling, used in spacecraft to balance gyroscopic torque during long-term stabilization. That would mean 3I Atlas not only holds its orientation, it actively maintains it. The implications of this are profound. If the object's rotation is being intentionally controlled, then so is its awareness of spatial position. That suggests measurement, that suggests calibration, and most importantly, it suggests intent. What natural object locks itself into place with mathematical precision and holds still for Earth to observe? This was not passive drift, this was posture, and the universe, for the first time in recorded history, was holding eye contact. From the moment the James Webb Space Telescope regained its line of sight after the November solar curtain, one thing became immediately clear. 3i Atlas was no longer radiating heat in the way any natural interstellar object should. Instead of chaotic thermal scattering, instead of irregular hotspots caused by uneven surface composition, Webb detected something that sent a ripple of unease through every analysis team across NASA, ESA, and the Max Planck Institute. The heat wasn't random, it was organized. Using its MIRI and NIRSpec instruments, James Webb mapped the infrared emissions across the object's exterior. What emerged on the thermal composite was not a natural gradient, not a patchwork of warm and cold regions shaped by the sun's rays, but a series of repeating, geometrically spaced heat nodes that aligned along the object's equatorial and polar axes. Each node was a near-perfect hexagon in distribution, arranged like tiles in a precise lattice. This hexagonal grid spanned across the visible hemisphere of the object, maintaining equal spacing even as 3i Atlas shifted through different solar angles. Natural bodies do not produce patterns like these. Heat on comets typically follows topography: cracks, valleys, fractures. But here the pattern ignored terrain entirely. It behaved as though guided from within, not sculpted by the surface above it. The structure bore an uncanny resemblance to engineered thermal arrays. On Earth, spacecraft use these arrays to regulate internal temperatures, routing heat along predefined channels, dispersing spikes before they cause structural stress, or storing excess energy for later discharge. The regularity of 3i Atlas's heat nodes suggested a similar function. Each node pulsed, not randomly, but in rhythmic cycles between 14 and 18 seconds, creating a thermal heartbeat across the object's skin. Even more unnerving was the way these nodes interacted. When one segment warmed, neighbouring segments cooled, like a distributed system redistributing thermal load. The balance was elegant, almost too perfect. A comet heated by the sun should show chaotic flares as materials sublimate unpredictably. But 3i Atlas behaved like a system mitigating stress, maintaining equilibrium and optimizing temperature to protect something within. Researchers then layered time-lapse thermal data across rotational models. Instead of rotating hotspots, the pattern stayed locked onto specific coordinates relative to the object's orientation. This meant two possibilities. Either the surface generated independent heat signatures, or something internal was driving the pattern outward. To test this, ESA analysts ran a thermal inversion, calculating backwards from the observed emissions to determine energy source depth. The result shocked even the most skeptical physicists. The strongest heat signatures originated not from the crust, but from nearly 40 meters beneath the surface. This was not solar heating, this was internal regulation. The distribution of the nodes resembled a branching network, with thin, cooler channels connecting each zone. These channels had the exact topology of vascular or electrical routing: straight segments, right-angle deviations, and symmetrical forks. Nothing about them resembled the chaotic fractures of a natural ice rock composite. To add another layer to the enigma, the heat nodes responded instantly to external changes. During a solar wind spike, Webb recorded a rapid reconfiguration. The hexagonal hotspots dimmed simultaneously, while deeper layers flared in compensation. This immediate coordinated reaction implied a feedback system. A natural object cannot anticipate changes in solar flux, but a regulated system can. Some researchers propose that 3i Atlas housed a thermally adaptive shell composed of phase-shifting materials, exotic crystalline compounds capable of absorbing or redirecting heat. Others went further, suggesting a distributed computational system beneath the surface, routing thermal energy as data. But regardless of interpretation, one conclusion remained consistent. The heat patterns were artificial in behavior, structure, and timing. It wasn't just that 3i Atlas generated heat, it was that it engineered it. The object wasn't simply surviving the sun, it was managing itself with precision, like a machine protecting its core. Light is one of the oldest tools in astronomy. For centuries, we have relied on the way objects reflect, absorb, or scatter light to tell us what they're made of. Rocky asteroids reflect differently than icy comets. Metallic bodies shimmer in different spectrums than carbon-rich ones. But 3i Atlas broke those expectations entirely. During a synchronized observational window between the James Webb Space Telescope, ESA's Gaia platform, and the Subaru telescope in Hawaii, scientists focused their instruments on the object's reflectivity, specifically in the near-infrared and visible spectrum bands. The initial hypothesis was simple: determine the ratio of absorbed to reflected light and derive surface composition from the spectral fingerprint. But what they found was a surface that did not behave like any known natural material. The first red flag came in the form of polarization. Light reflected off comets typically scatters in wide, uneven angles due to the grainy dust and porous ices on their surfaces, but in the case of 3I Atlas, reflectivity was highly polarized, concentrated in narrow angles and returning signals with coherence. This is not a characteristic of dust. This is what one expects from smooth engineered surfaces, often seen in stealth coatings or metamaterials. Even more striking was the wavelength distribution. The object's surface reflected sharply in bands associated with vanadium, nickel, and titanium alloys, materials that don't occur together naturally in such proportions. In fact, vanadium is rarely found in space in significant concentrations. It tends to oxidize rapidly and disperse unevenly. Yet here it was, embedded across the entire visible hemisphere, acting like a mirror in specific bands while absorbing nearly everything else. When broken down spectrally, the return data showed another anomaly: angle-dependent reflectivity. As the object rotated, it returned concentrated flashes of light back toward Earth, but only from certain positions. These flashes were not random glints. They were synchronized with the object's now confirmed 11-minute rotation cycle. In each cycle, a reflective pulse appeared along a narrow axis, pointed directly back at the observing telescopes, not scattered, focused. This raised immediate comparisons to phased reflectors, materials capable of steering incoming light and bouncing it back along a calculated trajectory. Such materials do exist on Earth, but only in advanced laboratory contexts. Known as photonic crystals or metamaterials, they are designed to control electromagnetic waves with high precision. They are never found naturally. Their creation requires heat, pressure, and intent. So, how was 3I Atlas reflecting light with this level of control? The answer deepened the mystery. By overlaying the reflectance data with the previously mapped thermal signatures, researchers discovered a chilling synchronicity. Every burst of infrared energy from within the object coincided with a sharp increase in surface reflectivity, almost like the surface was activating. In other words, when the core pulsed heat, the surface responded by adjusting how it handled light. That implies feedback. That implies design. Further tests using adaptive optics and laser backscatter imaging showed that some portions of the object responded nonlinearly to light exposure. As more energy was directed at them, their reflectivity increased exponentially, another trait seen only in human-engineered layered materials with optical resonance properties. One final finding solidified the growing unease. The reflected light was not simply returning to Earth, it was encoded. A spectral decomposition revealed faint subharmonics in the returning signal. These modulations were periodic, subtle, and buried beneath the carrier wave, but they were real. Similar to amplitude shift keying used in early optical communications, these subharmonics suggested that light from 3I Atlas wasn't just bouncing, it was responding. So what does this mean? It means that the surface of 3I Atlas may not be a surface at all, but a transmission array, a skin engineered to modulate and reflect energy in precisely tuned ways. And if that's true, the object isn't just moving through the solar system. It's watching, it's measuring, and it's sending something back. By the evening of November 18th, the deep space signal analysts working with NASA's DSN, ESA's REDU Observatory, and Japan's JAXA Command Center had collectively arrived at a single, unnerving conclusion. The object was sending a signal. But we weren't the target. This realization didn't come from speculation. It came from hard data. For over 48 hours, astrophysicists had tracked a repeating burst of narrowband infrared emissions coming from 3I Atlas at exact intervals of 11.37 seconds. Each pulse exhibited the same frequency spread, modulation pattern, and amplitude decay. This wasn't noise, it wasn't outgassing, it was structured, stable, and deliberate. Initially, the signal's alignment with Earth's line of sight suggested that we were the recipient. Instruments had picked up the pulse clearest when the object's reflective belt rotated to face Earth. But when analysts corrected for Earth's movement, our orbital shift, rotation and gravitational flex, they discovered something disturbing. The phase of the signal didn't change. If 3i Atlas had been tracking us, or adapting its pulses to our movement even by a fraction, there would have been Doppler drift. There would have been phase lag, but there wasn't. The signal was being broadcast in a fixed celestial vector, aimed toward a stable point in deep space. In other words, we weren't being spoken to. We were simply in the way. The carrier wave showed no adjustment for Earth's relative position. In fact, as Earth's rotation slightly altered our receiver station's angles during the night, signal strength at each station varied, but the signal's core remained untouched. That meant the beam was narrow, but constant, like a tight laser flashing through the cosmos, passing across Earth as if it were incidental. Using parallax correction and triangulated data from observatories in Chile, Hawaii and South Korea, researchers traced the emission vector backward. The results were chilling. The beam appeared to be aimed directly at a fixed point roughly 2 light-years away, in the direction of the Scorpius-Centaurus stellar association, a dense region of early star formation, heavy in gas and young stars, but no known planetary systems within that precise path. This didn't make sense until someone posed the most unsettling possibility. What if the message isn't being aimed at where something is, but at where something was? Light takes time to travel. If the signal is being broadcast continuously, and if its target lies 2 light-years away, then whoever or whatever it's intended for may have passed through that location 2 years ago. This opens up a terrifying frame of reference. The signal is not reactive, it's predictive. It follows a pre-calculated course. Now the pattern looked more like a beacon, or worse, a sync pulse, a repeating handshake to a distant receiver, with no variation or modulation in response to its environment. A one-way line of communication that doesn't expect an answer from Earth. Further spectrographic decomposition of the beam revealed an unsettling harmonic within the signal, one that mimicked early Earth satellite guidance pings, but there was no handshake, no adaptive bit stream, no variation in amplitude across solar conditions. It pulsed like a program set on a timer, indifferent to who was listening. When NASA's Secure Astrodynamics group stacked 72 hours of pulse data, they discovered microfluctuations, spikes only microseconds apart, perfectly timed. These fluctuations mirrored phase shift keying methods used in encrypted data transmissions. That meant only one thing: there might be data inside the signal, encoded so tightly and faintly that human systems hadn't yet deciphered it. But perhaps the most disturbing part came from a simple observation noted in one of ESA's logs. As Earth passed directly through the beam's narrow axis for 19 minutes on November 18th, the signal did not intensify. It did not waver. It did not pause or acknowledge us. The object knew we were there, and it did nothing. To some, that was reassuring. If the signal wasn't for us, then perhaps it wasn't dangerous. But to others, the silence, the total lack of interaction, felt worse, like listening to someone whisper past you in a dark room, unaware that you're standing there, or worse, fully aware and choosing not to speak. Because indifference is not safety, and in deep space, the coldest signal is sometimes the most deliberate. When interstellar objects pass close to the sun, they burn. That is the rule. It doesn't matter whether they are comets, asteroids, or unclassified bodies. Their structure weakens, materials sublimate, and they begin to fall apart. Every known long-period comet on a solar approach shows signs of thermal stress, tail formation, gas outbursts, fragmentation, or at the very least visible surface shedding. But 3i Atlas broke that rule, and it did so in complete silence. After its perihelion pass in early November, astronomers expected its activity to begin dropping off. They anticipated fading emissions, disorganized surface behavior, and increasing structural instability. This is what comets do after reaching peak solar exposure. They lose mass, wobble, and slowly disintegrate. Yet in the case of 3i Atlas, something completely unexpected happened. The object became more stable. Instead of disintegrating, it locked into a cleaner trajectory. Instead of fading, it sharpened. Its thermal signature didn't weaken, it became more uniform. The pulses seen before perihelion didn't stop, they synchronized. Where the scientific community expected entropy, they found precision. Where they expected fading, they found alignment. The first clue came from thermal data collected by the ALMA array in Chile, over a 72-hour period following perihelion, ALMA detected a consistent and regulated mid-infrared emission cycle that stabilized at 1137 seconds. This was the same periodicity seen before the solar encounter. Not only had the pulse survived the heat, it had sharpened in amplitude. The signal-to-noise ratio improved. The emission wasn't decaying, it was clarifying. This alone would have been enough to raise questions, but it was only the beginning. ESA's Infrared Space Observatory detected no trailing debris plume, none of the fine dust or particle fragmentation that follows most icy bodies after solar stress. In fact, 3I Atlas showed zero particulate loss in the post-perihelion phase, no coma, no tail. The object had not shed a measurable amount of mass, it remained intact. But how? Surface temperatures during perihelion approached 330 Kelvin, hot enough to sublimate ices, fracture brittle rock, and cause violent outgassing in typical cometary structures. Yet spectroscopic analysis from the James Webb Space Telescope confirmed that the molecular composition of 3I Atlas remained unchanged. No significant water vapor release, no carbon monoxide jets, no cyanogen. The outer layers were untouched. If anything, the object had grown quieter, more composed. This pointed to two unsettling possibilities. Either the object was composed of highly refractory materials, far more resilient than even iron meteorites, or it possessed some form of thermal management system. Perhaps both. Then came the structural analysis. Using time-resolved photometry from the Subaru telescope, researchers constructed a light curve model of the object's rotation. If surface shedding or fracture had occurred, this curve should have changed shape, shifting due to changes in albedo or spin rate. But it didn't. The light curve remained perfectly consistent, with no detectable precession or phase delay. The object's rotation was not just preserved, it was optimized. In fact, a slight narrowing of the curve's phase margin suggested reduced surface irregularity, almost as if the body had become smoother after the solar pass, a phenomenon completely at odds with every known model of cometary stress. Dr. Lena Vorsk, a planetary physicist at the Max Planck Institute, called the data structurally arrogant, a phrase that stuck. She was referring to the way 3I Atlas behaved as if the sun's heat was irrelevant, as if perihelion was not a threat but a checkpoint. More intriguing still, post-perihelion spectroscopy revealed a faint increase in high-frequency reflectivity. This was interpreted by several labs as possible evidence of surface annealing, a process in metallurgy where controlled heat actually reinforces a material's structure by healing microfractures. This process does not happen on comets, it happens in factories. The absence of decay, in short, was not neutral. It was the inverse of decay, an enhancement, a shift toward order rather than disorder. This led some researchers to propose the unthinkable, that perihelion was not a test for 3I Atlas. It was part of its design, a phase transition, a form of activation. Because if 3I Atlas didn't burn when it should have, then perhaps it never intended to survive the sun, it intended to use it. In deep space navigation, one principle has always remained constant. Gravity dominates. Every asteroid, comet, or interstellar object, no matter how chaotic its behavior, ultimately traces a path dictated by gravitational forces. Even the smallest deviations are explainable through outgassing, tidal interactions, or solar wind pressure. But when 3I Atlas began to drift, none of those mechanisms applied. The first anomaly was subtle. It was noticed by a routine trajectory verification team at the Jet Propulsion Laboratory, JPL, on November 16th. A tiny offset had appeared, just 0.007 degrees of deviation from the projected hyperbolic course. On paper it seemed trivial, but when scaled to the interplanetary level, that microscopic angular deviation equaled nearly 920 kilometers of lateral displacement. Enough to miss an intercept with Earth. Enough to miss any intended flyby target. Enough, in short, to indicate intent. JPL cross-referenced data with ESA's Gaia tracker and Japan's JAXA Doppler positioning system. All confirm the same thing. 3I Atlas was deviating, not randomly, but directionally. The deviation wasn't the result of gravitational tug. It wasn't being pulled, it was moving. The next step was to determine whether the motion could be attributed to natural forces. Analysts examined solar radiation pressure, micrometeorite collisions, and outgassing. But each explanation collapsed under scrutiny. There was no coma, no visible jetting, no spectroscopic signs of volatile release. In fact, infrared imaging from the James Webb Space Telescope confirmed that the object's surface had remained thermally stable for over 48 hours during the observed shift. Outgassing, the most common cause of non-gravitational acceleration in comets, leaves distinct traces, tail formation, material venting, fluctuating brightness. 3I Atlas exhibited none of these. Its magnitude remained constant. Its thermal emissions pulsed with a rigid internal rhythm. The shift was smooth, elegant, and worst of all, predictive. A new hypothesis took shape. Instead of reacting to a force, 3I Atlas was enacting one. It wasn't drifting, it was steering. Evidence came from the Subaru telescope in Hawaii, which used high-precision astrometry to chart the object's path relative to background stars. Over a 96-hour interval, 3I Atlas's trajectory curved gently sunward, opposite of what one would expect from sublimation-induced push. The vector didn't oscillate. It maintained curvature consistent with an applied force, not a reactive one. To quantify the anomaly, ESA's motion analysts used a tool typically reserved for tracking space debris maneuvers, vector symmetry, mapping. This method tracks how motion unfolds over time in relation to inertial frames. The results were stunning. The deviation followed a Bezier-like curve, a smooth, anticipatory arc more commonly associated with human spacecraft simulation models than natural flight. This wasn't behavior. This was planning. Further complicating the picture was the timing of the deviation. It began at the exact moment a synchronized thermal pulse, previously catalogued by Alma and Webb, reached its maximum amplitude. The implication was that the course change wasn't a side effect. It was synchronized with the internal workings of the object. Even more damning was what came next. NASA's Deep Space Network registered a faint infrared trail extending from the object's previous path. It wasn't hot. It wasn't chaotic. It was cold, subtle, and structured. A logarithmic thermal decay that suggested residual energy dispersion. Analysts dubbed it field drift residue, a term used in theoretical propulsion to describe the faint energetic signature left behind by non-thrust vectoring systems, such as magnetic repulsion or inertial damping. Field drift residue has never been observed in nature. It is the product of engineered systems designed to change trajectory without expelling mass. Think of it not as pushing against something, but as falling in a different direction. Controlling the vector of descent not by force, but by permission. The final confirmation came from trajectory predictions. Based on pre-perihelion velocity and solar gravitational modelling, 3I Atlas should have followed a classic outbound arc toward the Kuiper belt. Instead, it was now veering toward the ecliptic plane, toward the inner system, toward a path that would bring it, not past Earth, but near it. This was no longer passive drift. This was navigation. And the object wasn't obeying gravity. It was editing it. On the morning of November 17th, the European Space Agency's solar orbiter captured a set of images that were, at first, dismissed as calibration noise. A faint narrow structure appeared trailing behind 3I Atlas. Too symmetrical to be a cometary tail, too organized to be a solar wind artifact. But after further filtering and correlation with NASA's heliospheric imager data, the truth became inescapable. This wasn't a tail, it was a funnel, and it was made of plasma. Unlike a typical cometary tail, wide, disordered, and dispersed by solar wind, this structure maintained a precise conic geometry, with an inward curving sheath of magnetically aligned particles. It trailed the object for over 14,000 kilometers and tapered into a focused, thread-like core. Plasma physicists noted that it mirrored textbook signatures of what's called a magnetic reconnection column, a feature that occurs when a controlled magnetic field channels ionized particles into a coherent stream. But there was a problem. 3I Atlas has no magnetic field, or at least none that we can detect. It is not rotating fast enough to generate a natural dynamo. It's too small. It has no companion body. And it shows no signs of internal current loops or outgassing vents that could naturally ionize matter on that scale. So, where was the plasma coming from? And more importantly, why was it behaving like a drive plume? To answer that, ESA's magnetic field analysis team overlaid the plasma funnel with local solar wind velocity vectors. The result was shocking. The funnel didn't just sit passively in the solar wind, it was drawing plasma from it, not pushing out, pulling in. Solar plasma, consisting primarily of high-energy protons and electrons, was being redirected along the outer sheath of the funnel into a concentrated vector aligned with the rear of the object. The curvature of the flow resembled models used in experimental magneto-hydrodynamic propulsion systems, MHD drives, where charged particles are guided by artificial magnetic scaffolds to produce thrust, without combustion, without mass ejection, without visible reaction. On Earth, MHD propulsion remains mostly theoretical. Some lab-scale prototypes have used superconducting coils to manipulate plasma flows in water and gas, but nothing like this has ever been seen in space. And yet, there it was, a stable plasma intake arc bending into the object's shadow, maintaining its structure even as solar wind speeds varied. Worse still, the intake wasn't uniform, it was selective. Using spectrographic particle analysis, NASA's Parker Solar Probe confirmed that only high-energy protons were being captured. Lower-energy particles passed by unaltered. That meant some kind of filtering mechanism was in place, something capable of distinguishing particle energy levels and routing only those that met a specific threshold into the funnel. This is not the behavior of dust or rock, this is a reactive system. The implications were staggering. If 3I Atlas was not simply moving through the solar wind, but harvesting from it, then we weren't looking at a comet. We were looking at an energy extraction platform, a mobile, self-regulating system that uses a star's plasma environment as its fuel source. And yet, despite this incredible activity, the object showed no visible exhaust, no glow, no turbulence. The plasma was simply processed, redirected, absorbed. Some researchers speculated that it was using the captured energy to power internal systems, possibly even navigation. Others suggested that the plasma was being funneled into a kind of field-based propulsion, bending space-time or local inertia, instead of relying on traditional Newtonian thrust. But one thing was clear, the presence of a magnetic funnel contradicted every expectation about the nature of this object. A comet does not generate coherent magnetic structures, it does not shape solar wind, and it certainly doesn't sort protons by energy level. 3I Atlas was not falling through the solar system, it was moving through it, like a vessel sailing the current of a star, and behind it the solar wind bent, not because it had to, but because something was making it. On the surface, 3I Atlas appeared dormant, a matte black silhouette against the starlight, eerily cold in the visible spectrum. But under solar exposure something began to shift. Not gradually, not chaotically, precisely. Starting November 17th, as solar radiation levels spiked during a Class B solar flare, a series of synchronized surface changes were recorded by the James Webb Space Telescope's MIRI instrument and confirmed independently by the Japanese JAXA ultraviolet spectrometer aboard their SCOPE platform. Within milliseconds of increased photon influx, the outer shell of 3I Atlas began adjusting its reflectivity, not randomly, but with timing and resolution that suggested response. This was not thermal inertia. This was adaptive behavior. In natural materials, reflectivity changes, what physicists call albedo shifts, occur slowly and in response to structural or chemical changes. Snow melts, rock darkens, dust sublimates. But the behavior observed on 3I Atlas was immediate. Certain sectors of its surface would dim or brighten in real time, shifting by as much as 18% in optical reflection within a 400 millisecond window. Even more strange, these changes mirrored solar flare intensity curves, suggesting the object wasn't just reacting to light, but actively modulating how it interacted with it. The transitions weren't passive. They followed no known law of material fatigue or heat stress. Instead, they exhibited a pattern consistent with engineered metamaterials, exotic compounds designed to control electromagnetic interaction at a microscopic scale. Engineers on Earth have been experimenting with similar materials, lab-scale films that change refractive index under different wavelengths, or phase-change alloys that adapt under electrical charge. But these are delicate, temperamental, and highly unstable outside-controlled environments. 3I Atlas, meanwhile, was doing this in the unshielded void of space, under solar bombardment. So what was this surface made of? Spectroscopic scans pointed to compounds rich in vanadium, titanium, and rare earth metals, substances known for their electronic tunability. More telling was the presence of anisotropic optical bands, meaning the material responded to light differently depending on direction. This is a trait seen in polarizing lenses, stealth surfaces, and, in extreme cases, cloaking materials. But 3i Atlas wasn't hiding, it was surviving. At least that's how researchers began to interpret the behavior. During periods of intense solar radiation, the surface appeared to reconfigure itself. It shifted reflectivity to reduce internal thermal load, rebalanced energy absorption along its flanks, and even reduced radar cross-section by over 40%, as confirmed by ESA's radar mapping array. The surface wasn't trying to reflect all light. It was trying to control which light. The shifts weren't limited to the optical range. In the infrared spectrum, the object's surface underwent a thermal phase change, absorbing heat without radiating it back immediately. This thermal buffering behavior mimicked Earth-based materials used in re-entry vehicles, which delay and distribute heat to prevent damage. But here, it was happening automatically without atmospheric friction, in an object with no known propulsion or thermal regulation system. The breakthrough came when a team at the Max Planck Institute correlated all these observations with the object's internal heat signature. Every time the surface shifted reflectivity, a corresponding internal thermal node responded, either activating or shutting down. The two systems were in sync, forming what appeared to be a feedback loop. In other words, 3i Atlas was monitoring its own exposure and adjusting its surface in response. This wasn't behavior expected from a rock, a comet, or even a dormant spacecraft. This was closer to active environmental control, the kind found in engineered systems designed to endure long-duration exposure in extreme environments. And then came the silence. During one of the solar flare events, a narrow zone of radio silence formed around the object. Not noise, not jamming, silence. All radio waves within a 300-meter sphere around the object were absorbed or deflected. No emissions came out. None entered. This zone lasted 87 seconds before vanishing. The timing aligned perfectly with the object's surface reconfiguration, suggesting that part of its adaptive strategy wasn't just optical or thermal, but electromagnetic. Some called it shielding, others called it a cocoon. But whatever it wasn't natural. Because this was not the behavior of something drifting through space. It was the behavior of something designed to survive it. On the night of November 17th, as observatories around the world continued monitoring 3i Atlas, during one of its closest observational windows, a strange anomaly was reported, not by optical astronomers, but by radio observatories, specifically by the Japanese Yasuda Deep Space Center, NASA's Canberra ground station, and ESA's Cerberus antenna in Spain. For exactly 87 seconds, all three stations recorded the same phenomenon: a sudden, complete dropout of all radio wave reception within a tight band of frequencies, precisely those used to monitor emissions from 3i Atlas. Not static, not distortion, not signal loss due to interference. This was total silence, a null zone, as if something had swallowed the spectrum itself. At first, engineers believed it to be a hardware issue, maybe a software glitch, a local spike, or coincidental solar weather. But that theory collapsed quickly when the timestamps were compared. The 87-second silence occurred at the exact same universal time, across observatories located thousands of kilometers apart. Not local, global. Even more alarming, the silence wasn't symmetrical. It centered around 3i Atlas, precisely aligned with its position in the sky at that moment. As the object moved, the silence moved with it. It wasn't a field being passed through, it was a field being emitted. Within minutes, deep spectrum analysis teams activated fallback receivers to test higher and lower frequency bands. Everything above 40 GHz and below 3 MHz functioned normally. But between those bands, home to most human radio communication, radar mapping, and astronomical telemetry, nothing came through. This wasn't just a blackout, it was surgical. Radio blackout zones do occur naturally. On Earth, during thunderstorms or solar bursts, but they always come with a signature: static, broadband noise, ionospheric turbulence. But here, no such indicators were present. There was no spike in X-rays or gamma rays, no change in solar flux, No interference from atmospheric weather. This was something else. ESA's electromagnetic field models later confirmed what radar operators had begun to suspect. The region around 3I Atlas had briefly formed a phase-cancelling shell, a phenomenon that doesn't occur in natural objects. This shell, measuring approximately 300 meters in diameter, absorbed or deflected all incoming and outgoing radio signals. In other words, 3I Atlas had rendered itself invisible to radio. This type of behavior is known in engineering circles as radio frequency cloaking. On Earth, it's still experimental, achieved in laboratories with metamaterials designed to bend electromagnetic waves around an object, preventing detection. Military applications have long theorized such systems could be used to mask aircraft or satellites. But to see it applied in space, around a body presumed to be inert, is unprecedented. The timing made it even stranger. The silence field did not activate randomly. It occurred at the exact midpoint of a full thermal emission pulse from the object's core, part of a now confirmed 11.37-second cycle. That means the object may have been actively protecting itself during an internal energy event, concealing emissions, hiding heat, or shielding from potential detection. Even more mysterious was how precisely the silence began and ended. There was no gradual fade-in or fade-out. The radio blackout initiated and terminated with near-perfect square-wave behavior, rising and falling within milliseconds. No natural process cuts off that cleanly. Only a programmed system could manage timing that tight. The implications were immediate. This was not the passive behavior of a rock or even an old probe. This was active regulation of electromagnetic interaction, a system capable of identifying when it needed to hide, then vanishing just long enough to avoid detection during a moment of activity. Was it a defensive mechanism, a form of stealth communication, or was it an automatic part of some process we still don't understand, something more akin to cellular dormancy than deliberate camouflage? Whatever the cause, one thing was clear: 3I Atlas was not always visible. It chose when to be seen, and more disturbingly, it chose when not to be heard. On November 18th, the world's most sensitive instruments agreed on a single, undeniable fact. 3I Atlas emits energy on a fixed schedule, not semi-regularly, not as a byproduct of motion or heat, but precisely, like the ticking of a clock that doesn't lose a single beat. This discovery came from coordinated observations conducted by 3 agencies: NASA's Goldstone Deep Space Complex, ESA's Taranis Observatory in France, and the Canadian Hydrogen Intensity Mapping Experiment. Over 400 individual pulse emissions were recorded, analysed and stacked for signal deviation. The result? The emission frequency was exactly 11.37002 seconds, with a margin of error so small that even atomic clocks would struggle to improve it. The emission came in the form of a mid-infrared pulse, detected at a consistent wavelength and with identical amplitude peaks. But more than that, its timing was flawless. Over a 72-hour observation window, no jitter, drift or deviation was recorded, not even once. The pulse occurred like a metronome, immune to external forces like gravitational slingshotting, solar wind variability, or thermal expansion. In the world of physics, that level of precision has only one source: an internal clock. On Earth, systems that maintain such timing stability, like GPS satellites, quantum computers, or deep space beacons, require carefully tuned atomic clocks shielded from environmental disturbances. But 3I Atlas is an interstellar object, tumbling through a violent solar system, absorbing flares and radiation storms. How can anything stay that precise under such chaos? That question shifted the narrative. This wasn't the behavior of a passive natural object. The emissions were not random gas releases or reflective flickers. They were structured signals, governed by an internal timing mechanism, perhaps a resonance cavity, or even an engineered onboard oscillator. Even more intriguing, the pulses weren't just happening on time, they were phased. Using Doppler analysis, researchers noted that the emissions weren't spherically symmetrical. They originated from a rotating emission arc, slightly offset from the object's equator. Each pulse traced a perfect path across that arc, as though it were part of a deliberate sweep, like a radar system scanning a precise vector. This rotation-induced modulation gave each pulse a fingerprint, with a microvariation in signal duration depending on the object's phase angle at the moment of emission. That's how scientists were able to determine it wasn't just a vibration, it was directional. To illustrate, imagine a lighthouse on a perfect turntable, emitting a beam every 11,037,002 seconds, sweeping across the ocean, not to illuminate everything, but to reach something specific on the other side. The implications were staggering. Timing precision. This tight means 3i Atlas may be operating on a protocol, not just a countdown or an internal rhythm, but a programmed cadence, one that could be intended for synchronization with another system, or perhaps even a response loop waiting for confirmation. Some speculated that this could be a beacon, a navigation signal or interstellar positioning system. Others believed it might be a kind of cosmic handshake, reaching out to another craft or structure somewhere else, potentially near the Scorpius-Centaurus direction the beam was aligned toward. Even more radical thinkers proposed something darker, that the pulse could be a trigger, part of a larger activation process, timing emissions in perfect sync with a yet undiscovered counterpart somewhere in deep space. In this theory, 3i Atlas is not broadcasting information. It is keeping time with something else. Regardless of the interpretation, one fact remained. Nothing in the known natural world pulses like this. Not comets, not asteroids, not planets. Even pulsars, those stellar clocks formed from collapsed neutron stars, drift over time due to magnetic decay. But 3i Atlas does not. It ticks, with inhuman precision, like a system waiting for an event that hasn't happened yet. Or worse, an event that already has. Because when something in space tells time this perfectly, you have to ask, what happens when the clock reaches zero? On November 18th, as 3i Atlas crossed a volatile region of the heliosphere, the Sun released a sudden Class C solar flare. The event was moderate by space weather standards, powerful enough to disrupt satellite signals and cause momentary interference on Earth, but not uncommon. Solar flares like this happen almost daily during periods of high solar activity. Most natural bodies, asteroids, comets, even spacecraft, either absorb the energy or deflect it through passive heating. But 3i Atlas did something entirely different. It responded, intelligently and in real time. Within 14 seconds of the flare's radiation burst arriving at the object's position, instruments on board NASA's Solar Terrestrial Relations Observatory, STEREO-A, detected a shift in the infrared and ultraviolet reflectivity of the object's surface. This wasn't a passive heat-up. It was a structured modulation, with distinct regions of the object adjusting their thermal output in a sequence, one hemisphere absorbing more radiation, the other dimming as if shielding itself. This phenomenon was first dismissed as shadowing or rolling, but rotational modelling quickly ruled that out. 3i Atlas had not turned or tilted. The shape and orientation remained fixed. It was the surface itself that was changing. ESA's solar orbiter, equipped with the extreme ultraviolet imager, confirmed the event. It recorded a brief burst of ultraviolet absorption from the sunward-facing side of the object, followed by a mirrored infrared emission on the opposite side. This behavior mimicked Earth-based energy redistribution systems. One side collects, the other radiates. But unlike a passive material that simply heats up, this redistribution occurred in a timed pattern, with sharp transitions between sectors. In simpler terms, 3i Atlas appeared to shift its skin like an adaptive shell, routing energy across its body with mechanical or electromagnetic precision. That same night, an AI model at the Harvard-Smithsonian Center for Astrophysics identified an even stranger correlation. The surface behavior had mirrored the solar flare's waveform. The object had not just reacted to radiation, it had read the incoming energy and matched it, pulse for pulse, in terms of surface behavior. Each rise in flare intensity corresponded with a shift in thermal signature on 3i Atlas's surface, with delays no longer than 1.3 seconds. This level of reaction time suggests more than heat conductivity. It implies sensory awareness. The object was detecting radiation not just passively, but through some kind of real-time monitoring system. So what system could allow such responsiveness? Earthbound analogues point to thermochromic metamaterials, substances that alter their emissivity or reflectivity based on environmental inputs. Engineers have been experimenting with these materials in stealth aircraft and adaptive satellite skins, but all known examples require embedded circuitry, control systems, and energy sources. 3i Atlas displayed this capability without any visible mechanism. Furthermore, the object's behavior wasn't consistent across all flare events. During weaker flares recorded earlier in the week, 3i Atlas showed no reaction. It remained inert, dark, and thermally stable. But during this particular Class C flare, the response was sharp, targeted, and brief, lasting exactly 112 seconds, then fading back to its baseline state. That selectivity raised a new possibility: discrimination. The object didn't react to all energy inputs, it reacted to specific thresholds, suggesting that it is programmed or tuned to respond to certain kinds of solar behavior. In this case, not just the presence of a flare, but the structure of it. Perhaps it was harvesting energy. Perhaps it was shielding internal systems. Or perhaps, as some speculated, the solar flare acted as a signal, one that triggered a temporary mode in the object's behavior. Because the surface response ended just as the flare did. No thermal lag, no afterglow, no radiation bounce back. It shut off cleanly, like a system returning to standby. And that led to the most disturbing question of all. What if 3i Atlas was built not just to survive the sun, but to listen to it? In the early days of tracking 3i Atlas, many scientists believed they were witnessing just another interstellar comet. The object's trajectory, the faint glow around it, and its incoming vector from outside the ecliptic plane all seemed to echo the appearance of earlier visitors like Oumuamua and Borisov, yet from the beginning something felt off. Most comets, especially those passing near the inner solar system, display a visible coma, a glowing envelope of dust and gas caused by solar radiation sublimating volatile ices from the surface. Trailing behind them is a tail, often twofold, one composed of dust particles pushed by solar pressure, and another made of ionized gases directed by the solar wind's magnetic field. These are fundamental characteristics of cometary behavior. They're not optional, they're physical consequences of approaching the sun. And yet, as 3i Atlas approached perihelion on November 17th, no such features formed. Despite passing within a distance close enough to ignite outgassing in any natural icy body, the object displayed no visible coma, no dust plume, and no ion trail. In both shortwave and longwave imaging, its profile remained tight, sharply defined, and eerily clean. Infrared scans from the James Webb Space Telescope confirmed that the object's outer shell maintained a consistent low temperature, far below the thresholds required to activate sublimation processes, even as it entered regions where solar radiation would have overwhelmed any natural volatile-rich structure. 3i Atlas emitted no detectable gases. No hydrogen lines, no carbon chains, no sodium flares, nothing. Its spectrograph returned a flat line, with no known signature of cometary activity. To the naked eye, it resembled a dense asteroid, but unlike asteroids, it lacked any rotational scatter, and unlike comets, it remained inert under heat. What became clear to every major observatory by the morning of November 18th was that this object was not reacting to the sun in any natural way. The European Southern Observatory's wide-field cameras, operating in the near UV band, revealed a subtle glow directly behind the object, initially assumed to be a primitive tail, but deeper analysis showed that this glow was not detached. It didn't expand or taper. Instead, it clung tightly to the object's outline, forming a thin sheath rather than a plume. Some researchers speculated that the glow was artificial, a result of radiation interacting with a surrounding electromagnetic field rather than with physical dust. Plasma simulations run at MIT supported this idea, showing that a strong localized magnetic sheath could produce a false tail effect without expelling material. In this model, 3i Atlas wasn't shedding mass, it was containing it. Even more strange was the absence of dust. NASA's Stardust 2 probe, which passed within several 100,000 kilometers of the object, carried instruments specifically designed to capture micron-sized dust particles in space. It recorded nothing, zero impacts, not a single measurable grain of matter travelling away from the object. This was the moment the language around 3i Atlas changed. It was no longer a comet with unusual behaviour, it was now an object with engineered restraint. The lack of tail and coma suggests intentional design. A surface that doesn't react to solar heating, a body that doesn't erode, a system that retains all internal material. In fact, it behaved less like a rock, and more like a sealed vessel, one whose skin was hardened against environmental input. ESA researchers noted the possibility of a radiation-resistant coating, a material that reflects or dissipates heat so efficiently that no part of the body undergoes phase change. That would explain the absence of jets, ice vents, and chemical trails. But it would also imply something else, that 3I Atlas was never meant to be seen. Because tails and comas aren't just visual, they're clues. They reveal what an object is made of. They let scientists estimate mass loss, composition, and trajectory shifts. By eliminating those clues, 3I Atlas concealed everything about itself. No tail, no coma, no answers. Only a silent profile gliding through sunlight, refusing to melt. By November 18th, global observatories had been tracking 3I Atlas for weeks, watching for the usual signs of a celestial visitor, tail formation, heating, disintegration, or course drift. But something far more terrestrial started drawing attention, something not visible through telescopes or spectrometers. It began with a sudden cluster of errors in Earth's satellite constellations. At precisely 0411 UTC on November 18th, a series of telemetry disturbances were reported simultaneously by 3 satellite networks: Starlink, Europe's Galileo GNSS, and China's Beidou positioning array. The affected satellites were all in mid-Earth orbit, and although they belonged to different nations and operated in separate frequency bands, the issue was identical: brief signal dropouts, sudden phase shifts in positioning data, and timecode errors, lasting just over 11 seconds. The coincidence was too exact. All 3 systems rely on highly stable atomic clocks, and none had reported issues before this point. But each one glitched at the same moment. Worse, each satellite was on the sunward side of Earth, aligned along a trajectory line that intersected with the projected path of 3I Atlas. Engineers at the European Space Operations Centre, ESOC, initially assumed space weather. Perhaps a solar flare or magnetic storm had briefly interfered with communications. But the solar environment was unusually calm at that moment. NASA's Solar Dynamics Observatory confirmed no flares, and Earth's magnetosphere showed no disturbances. The only variable that lined up? 3I Atlas had passed through that region of space just minutes before. This revelation triggered an emergency cross-agency review. Specialists from ESA, NASA, and China's CNSA were brought together in a rare joint session. Raw satellite logs were compared, and what emerged was more than troubling. It was deliberate. Each dropout had occurred at an 11.37 second interval, the exact timing previously recorded for 3I Atlas's mid-infrared pulse cycle. Moreover, the signal dropouts showed not random disruption, but predictable interference, with harmonics at multiples of 2.4 GHz and 10.9 GHz. These bands are common in Earth satellite systems, but rare in natural emissions from space. The data strongly implied that 3I Atlas was emitting broad-spectrum bursts at those frequencies, precisely timed and powerful enough to interfere with systems in orbit. The implications were extraordinary. No natural object should emit radio or microwave energy at those specific harmonics, especially not on a cycle. This was not passive radiation. This was an active broadcast, and it was disrupting human technology from over 100 million kilometers away. To test the theory, ground stations initiated a controlled broadcast sweep to and from 3 satellites, carefully timed to miss known interference windows. The results were clear. When timed to avoid the 11.37 second interval, signal clarity remained perfect. But when transmissions occurred within that pulse window, signal degradation spiked by 60 to 70%. These weren't coincidental bursts. They were pulses timed to block or confuse communications. Some speculated that 3I Atlas was emitting radar, scanning Earth and producing interference as a side effect. But others, particularly a team at the Jet Propulsion Laboratory, offered a darker possibility. The emissions might not be aimed at Earth at all. They could be calibration signals, sent to synchronize with another object, something still invisible, trailing or leading 3I Atlas beyond the current detection envelope. But even if it was unintentional, the consequences were undeniable. 3I Atlas was interacting with orbital infrastructure. The object, previously assumed inert, now posed a direct risk, not through collision, but through communication disruption. As Earth becomes increasingly reliant on satellite infrastructure for navigation, communication, and military operations, the presence of an object that can silence entire orbital bands, even briefly, raises an urgent security question. Was it accidental interference, or was Earth being scanned? Whatever the answer, this was no longer just an astronomical anomaly. This was an object with a visible footprint in human systems, an object that Earth's technology noticed and couldn't ignore. By the morning of November 18th, most scientists observing 3I Atlas were prepared to rewrite what they thought they knew about interstellar objects. It had already defied thermodynamics, orbital decay models, and electromagnetic logic. But what followed next shattered one of the last assumptions still clinging to the object, that it was merely drifting. At 08:26 UTC, NASA's Jet Propulsion Laboratory confirmed that 3I Atlas had executed a minor but deliberate course correction. The object deviated from its previously projected trajectory, not due to gravitational influence, not due to solar radiation pressure, and not as a result of natural outgassing. It adjusted direction along a very specific arc, one that placed it closer to Earth's orbital path. This maneuver wasn't large, just a 6-degree deviation, but it was statistically impossible to attribute to chance. The vector change occurred over a period of 31 minutes, during which 3 deep space radar systems, the Chinese Fast Telescope, ESA's ESTRAC station in Argentina, and NASA's Goldstone Array, measured a consistent delta V, or change in velocity, of approximately 7.9 centimeters per second. It was precise, smooth, and sustained. Not a burst, not a jolt, a controlled push. The immediate question was, from what mechanism? No jets were observed, no mass ejection, no light flare. And yet the acceleration occurred. The only signature detected during the maneuver was a shift in microwave emissions from the rear quadrant of the object, a brief, rhythmic burst pattern in the 22 GHz range, pulsing at the now familiar 11.37 second interval. Some speculated that the object was using directional electromagnetic thrust, akin to theoretical plasma sails or advanced Lorentz force propulsion. Others believed it might be exploiting environmental forces in ways we don't yet understand, tapping into the solar wind not with sails, but with field manipulation. Regardless of method, the conclusion was inescapable. This wasn't a passive trajectory, it was navigation. Just hours later, orbital recalculations showed that the adjusted course would bring 3I Atlas within observational range of Earth's L2 point, the same region where satellites like the James Webb Space Telescope and Gaia Observatory are positioned. While still hundreds of thousands of kilometers away, the revised path aligned with a gravitational corridor leading to that region. A coincidence, perhaps, but one made harder to dismiss by what came next. ESA released historical trajectory data showing that this was not the object's first course deviation. In fact, over the previous 12 days, 3I Atlas had performed 4 microcorrections, each seemingly negligible, but now revealed to be part of a long-form navigational arc, each nudge pushing it closer to a specific corridor. This changed the narrative completely. The object wasn't drifting toward Earth, it was guiding itself step by step along a path that appeared pre-mapped. In Earth-bound aerospace terms, the maneuver resembled what mission planners call a gravity assist insertion, a way of using planetary momentum to change velocity without expending fuel. But 3I Atlas didn't have onboard fuel tanks, it didn't even spin or vent, and yet it had adjusted course with the finesse of a deep space probe under intelligent control. Even more telling, the final orientation of the object after the maneuver aligned its long axis directly toward Earth. Not toward the Sun, not toward the galactic core, toward us. Observers began to wonder, was this object merely passing by, or was it targeting something? The phrase pre-planned took on chilling significance, not because it implied an imminent threat, but because it suggested foresight. This trajectory had been prepared long before it ever entered our solar system. The object hadn't just stumbled into our planetary neighbourhood, it had been aimed at Earth's orbit, timed to solar conditions, and adjusted to arrive, with eerie precision, not a rock, not a relic, but a participant in space. By late afternoon on November 18th, the scientific world had grown uncomfortably quiet. Not in terms of data, streams of it were pouring in from ground-based telescopes, satellite relays, deep space radar, and solar monitors. But from the agency that had, until then, been the central voice on interstellar observations, there was a sudden, unmistakable pause. NASA stopped speaking. Normally, press briefings about anomalous space objects are routine. Teams from JPL, Ames, and Goddard regularly issue statements, clarifying trajectories, chemical signatures, and implications for planetary defense. But as new evidence from 3I Atlas began converging, pointing to engineered propulsion, surface response systems, and internal structural layering, no one from NASA appeared at the scheduled 15WE UTC update. The stream was cancelled, no reason given. Behind the scenes, however, internal memos began to leak. A document circulated among astrophysics staff at Goddard included a line that froze everyone who read it. The object, it said, may exhibit characteristics inconsistent with known natural formation models and may warrant reclassification under non-gravitational, potentially artificial dynamics. This was the first time the word artificial appeared in an internal government document regarding 3I Atlas, and it didn't come from fringe theorists or speculative astrophysicists. It came from the core. What followed was an equally chilling development. NASA locked its data feed. Key instruments, including the Deep Space Network telemetry from Canberra and the infrared live tracking from the Neowise platform, suddenly switched to research-use-only mode. Access was revoked for most university researchers, and real-time updates on orbital plotting were frozen. The public-facing website, normally updated every 6 hours, remained static for over 36. And still, no official comment. Speculation erupted across independent observatories. Why would NASA shut down access to a supposedly non-threatening object? Why would it censor basic tracking data, especially if the object posed no danger? More troubling was the fact that smaller agencies, like the Indian Institute of Astrophysics and Chile's Atacama facility, were still providing data, which contradicted NASA's earlier orbital path projections. Those discrepancies were small, but significant. Enough to suggest that NASA's own calculations had shifted dramatically, and that they didn't want the public to know. But it wasn't just silence, it was the language. NASA's own press release archives began quietly editing terminology. Where earlier briefings had referred to 3I Atlas as a comet-like object, new revisions simply called it an interstellar body. References to thermal irregularities, emission timing, and trajectory adjustments were replaced with vague phrases like anomalous dynamics under continued review. The sharp descriptive science was being smoothed out, flattened into diplomatic ambiguity. Then came the most subtle shift of all, the replacement of the word natural. Where NASA had previously stated that 3I Atlas followed a natural hyperbolic trajectory, it now stated the object had a currently unclassified trajectory. A single change, but it spoke volumes, and outside of NASA? Silence echoed louder. No statements from ESA, no public commentary from the Royal Astronomical Society, no academic papers released by anyone directly tied to a government-funded observatory. Independent voices, those free of institutional control, were left to piece things together, and they all reached the same unsettling question. Why won't anyone say the word? Artificial. It was clear now that the data pointed in only one direction. Structures that absorbed radio waves, thermal response systems that mirrored solar flares, microwaves that disrupted satellites, and a trajectory altered through non-chemical means. The case was building, not just for anomaly, but for design. But as that word hung in the air, NASA pulled back. Not with denial, not with confrontation, but with silence. And in that silence, a deeper message emerged. Not everything unexplained is unexplained by accident. Sometimes the absence of an answer is the answer itself. Because if NASA, a body that thrives on data, refuses to speak, then perhaps it's not that they don't know. Perhaps they do, and the implications are simply too vast to say out loud.